Hello, everyone. Welcome to Brunel's virtual open day course talk for Aerospace Engineering MSc. And I'm Maya Editor, and I'm going to be giving a very brief introduction into the program here at Brunel. So, my area of expertise is in computational modeling of solid mechanics and fluid dynamics. And as I said, I'm also the course director for the Aerospace Engineering MSc. So, during my brief talk, I will introduce the university very generally, and then I'll focus on engineering at Brunel. Then I'll talk a little bit more about the course, some of the different modules you can have, or that you do have, sorry, should I say, in the course. And then the accreditation the program holds. And then we'll talk about some of the facilities that you might use while studying here. And then I'll just pick some examples of MSc projects that you could have if you were to study the aerospace MSc program here at Brunel. So Brunel University, for people who might not know the university, is a research-intensive university. Dates back to 1966, at least as a university, and it is highly ranked. So it's ranked 204 in the world, and that's the aerospace, mechanical and aerospace engineering degree is quite highly ranked in the world. And we also, another key feature for us is our international students, the community, the student community we have, how diverse it is. So we have over 2,000 international students, and they all come from over 150 countries. And this is something that's been recognized even in the international outlook of the university. So it's Brunel is ranked fourth in the UK for its international outlook, and 20th in the world, again for its international outlook. So that's a good thing. We have quite a diverse student community. It's also a single site university, which is a very good thing and very hard to find in London, especially. So it's a one campus with thousands of, several things all around you that you need. Everything you need is literally on campus and within 10 minutes walk. Then you also have, of course, the tube, which takes you, the underground, a train which takes you straight to central London, if you so wish to do so. And talking a little bit more on engineering at Brunel. So engineering at Brunel is I would say, the biggest degree really, or discipline here at Brunel. Even Brunel itself is named after an engineer, a British engineer, very, very good, very strong British engineer, well known for several developments and several constructions that he designed and built. So that's a good thing. And what that means then, of course, is that we have several research that's ongoing that are international leading. We have very, very good labs, very strong links with industry. Now, some key research areas that we are certainly good at would fall within computational solid mechanics and computational fluid dynamics, which are the areas I sort of work in. Then we also have aeroacoustics research area, and we also have experimental aerodynamics, which is ongoing within the department. We also have advanced powertrain and fuels and energy futures. These are different research aspects, and you can certainly see where this feed into the engineering discipline just by the name itself. So these are areas that we certainly can say that we're quite strong in, and we have academics who are actively researching in that area. But a little bit more about the course itself. So Brunel MSc in aerospace, what we aim to do is to develop students who are industrial ready, so industrial ready engineers who can come out of, once you finish, come out and meet the growing demand within the industry and the society. And I say growing demand because that really is the case that we have at the moment. So I've got some pictures there, which will start to explain the growing demands that we have. So automotive, for example, it's a growing industry. it's a shift in industry. Things are changing. The way automotive, the design of cars and several other designs within the industry are changing quite drastically. AI is coming in, electric cars are coming in, electric infrastructure is needed. Certainly, zero emissions or lower carbon footprint is a very strong force within the engineering discipline, and that's changing a lot of things everywhere. So there's a lot of demand for engineers that can actually create this change that the society needs. I've got another picture there, which is a supersonic aircraft, which is one of the NASA concepts, because of course supersonic aircraft is something that's a sort of with Concorde anyway had stalled, but there is a very good chance that it will come back again. And there are several companies that have several concepts ready and being tested. So again, this is another, in aerospace, for example, it will need engineers to meet the need here. And the need here, of course, is the fact that when you're traveling, you don't want to spend, you want to get to where you're going to quickly. There is that time essence sometimes. And then you also have, and I always love this picture to the bottom right corner. And these are our students, engineering students, during the COVID pandemic. And, they're, of course, studying either automotive, aerospace, or mechanical. But what they find themselves doing in this image, as you can see, is using their skills to meet a demand that just came up. Society wasn't ready for that demand, but they rose up and fit, and they fit that gap and delivered there. So that the student there is designing the visors that covers the face of or protects the individual from COVID, and is designing the visor holder on in CAD, and those design or the CAD design was then fed to 3D printing machines, and then you can see the students assembling that in the lab. So that's a very good example. I think it doesn't get any more succinct than that to say that we create industrial ready engineers who can literally meet the demand and as it unfolds. So what that means then is the course is designed to equip postgraduate engineers with, first of all, a good grounding in fundamental principles, the science and the practical skills, which we teach right through the taught modules. So if you were to study MSc here, during the whole program, you will be taught through lectures, seminars, lab sessions, talks, and workshops, all of which at present are face to face. During the course, you will be involved in practical and challenging projects. So we have two main projects. We have the group project, and I'll show some examples of a group project. I'll talk about it a bit later, where you work with your colleagues and you have a big task at hand. And then you have your individual project, which again, I'll give some indications as to what these could look like. And these are certainly the individual one are usually, linked to a certain research that's ongoing at the moment. You can also suggest a topic, but you do have to link it with an academic within the department who has expertise in that area. Another thing to mention about the course is at Brunel, we definitely hold a very strong idea of students designing, building, and testing their design. So we expect our students to go through the whole design loop to complete the design loop, which is they do their design, they come up with a concept, they do all sorts of simulations, calculations with their fundamental scientific background or scientific principles, and then they make several predictions as to, regarding how the concept will behave, how it will perform, and then we expect them to build it and then to test it as well to confirm that their predictions are accurate and indeed the design is a valid design. There is also, of course, a main focus on innovative solutions in all these projects. Now, just to talk briefly about the different modules themselves. So we have, first and foremost, the whole MSc itself accounts for 180 credits. And you have to complete that for you to, of course, to complete the MSc. You get to choose, you get some options of two modules. You get to choose two out of the four modules shown. And each of these four carry 15 credits. So when you choose two, you get 30 credits in total. So the first one, of course, is design and analysis of aircraft. Then you have fluid structure interaction and aeroelasticity. So these two are really geared towards earthbound or atmosphere, or sorry, earthbound aircraft vehicles, or aircraft that fly through the atmosphere. So the first, of course, is quite self-explanatory: designing and analysis of aircraft, which is conceptual design and analysis. And then the second one, which is my module, is looking at fluid structure interaction and the fact that when we design an aircraft wing, for example, we do all sorts of analysis on the aerodynamics. We do all sorts of analysis on the structure, but then we have to realize that the structure itself is flexible. So when you do have the aerodynamic loads, the structure will deform, and that in itself will change the load again in a coupled fashion. So we have to be very careful with this to make sure structures are certainly stable. Then the other two are geared more towards space-bound vehicles or spacecraft. So the first is design and analysis of spacecraft systems, and the second is space dynamics and propulsion. So you get to choose two out of these. You can mix and match them as between the space-bound vehicles and also the earthbound vehicles. It might not be the best way to do it. The best way might be to focus more on the space or to focus more on the earthbound vehicles, but that is entirely up to you. Then we have these other four modules, which is strategy and business planning, advanced aerodynamics and propulsion systems, advanced solid body mechanics and FEA, and current topics in aerospace and advanced CAD. Now, these four are compulsory. They are 15 credits each as well. And again, the topic might explain exactly what it entails here. So the strategy and business planning looks more towards the business side of engineering and the management of engineering. Then, of course, advanced aerodynamics and propulsion system, as the topic says, goes more into scientific concepts in aerodynamics, more advanced scientific concepts, and also propulsion systems. Then the third is, of course, your solid body mechanics and finite element analysis. Now, the fourth one is a module, sorry, that is quite unique to our program here at Brunel. So, current topics in aerospace is a module that does not teach fundamental scientific principles, in that it doesn't teach theory. What it does is it focuses more on the current topics that are driving the industry, the current trend that we're seeing within the industry, within the aerospace industry. So there you will have several guest talks, guest lecturers or guest speakers from industry that comes to talk about the things that are driving the industry at the moment. And this is a module where we're trying to bring you up front to the current trend at the moment, so you are abreast with it and you know exactly what's going on at the moment. Worth mentioning as well when we talk about guest speakers, so in my module, which is FSI, Fluid Structure Interaction and Aeroelasticity, we do have industrial speakers there as well, from Airbus, that comes to talk about things like gust and how they include gust. When you have gust, you have a lot of load from the gust that goes into the structure of the aircraft, and there's a way in which the aircraft design can limit these loads. So they give a talk about that and other aspects of aircraft design as well. Now, the last two major group project, that's the first one is major group project, which, as I said earlier, you will have a group project where you work with your colleagues on a particular topic. That carries 30 credits. And then you have your final dissertation, which is the huge module. It's not really a module, it's actually a project. It's an individual research project. And it's, it'll have a very, it'll have a topic So we have several topics that are released every year, and students get to pick from them. So at the moment, the students that are here right now, they're picking their modules and the topics they want to research in. And then each topic has an academic attached to it. And of course, around about March, they can start to do their project, and they do that all the way through summer until September. It's a research project, so it's usually linked with ongoing research within within the department. Now, as I said earlier, you can suggest a topic. That is possible. Sometimes we have students that just have a very good interest, a very strong interest of theirs. But what you have to do is link it with an academic whose area of expertise falls within the or in whose area of expertise the project falls within. Now, the Aerospace MSc program is accredited by two bodies. The first is the Institution of Mechanical Engineers, the IMechE, and it's also accredited by the Royal Aeronautical Society. So accreditation basically just means that these bodies have certified that they certify the program, and also that means that if you were, you know, aiming towards chartership, which would most likely be awarded by either of these two bodies, doing this MSc program will certainly get you closer to your chartered status. You need that. You need that acknowledged for you to be able to achieve your chartered status. And it just means, of course, that the standard has been certified and it's met the 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 standard set by this institution. And also, I mean, the program holds the longest certification duration that they can award. Now, talking a little bit about facilities, there are different facilities within the department. You might not get to see all of them, and it's also not an exhaustive list. We can't really give an exhaustive list here, but these are the ones that I think you may actually come across either in your project or your group project or your research project, or just in your module perhaps. So the first is computational. So computational modeling and simulation is a big thing for us. And if you remember, I mentioned it's a strong research area for us. So we have several state-of-the-art computational labs, and we have access to very high performance computers or clusters or HPC. So we have one locally at Brunel. If you were running a simulation, say for example the CFD analysis on a Formula One car, for example, you might not be able to run that efficiently on a desktop computer. So you might need access to a HPC. So there is one at Brunel that you can have access to. There's also one that's a bit more nationwide, much more powerful, thousands and thousands of cores. Again, we have access to that at Brunel as well. Then there is the wind tunnel. So we have quite a few wind tunnels actually. This says 3 subsonic wind tunnels, but there's been an addition of 2 subsonic wind tunnels, so that makes 5 subsonic wind tunnels. And we also have a supersonic wind tunnel that goes up to Mach 1.8. Then we have an anechoic chamber, which is a specialized type of wind tunnel in which you don't have sound bouncing off the walls. So if you were in an anechoic chamber, which is a wind tunnel, as I said, you'll feel, or you'll hear the difference in the sound, because when you speak, the sound propagating from your mouth does not bounce off the walls. So it sounds it sounds very different. Now that equipment, or the wind tunnel, is for specialized type of experiment, and this experiment where you are interested in aeroacoustic sounds. You're trying to measure perhaps the source of aeroacoustic sound. So if you've ever been most likely been on an aircraft, you'll hear how noisy it is. Every single noise you detect and you pick up as an aeroacoustic, or has an aerodynamic has been originated from either the wings or the engine. So it's aeroacoustic sound. And when we're trying to do this experiment, we're trying to understand the sources of this sound, and of course, we're trying to minimize them or reduce them. So we have to understand where the sound is coming from and where it's originating from. And then we also have engine test labs. I should say there are actually some pictures that showing all of these. So we have an engineering test lab, which is in the next pictures, but we have a driving simulator, a flight simulator, and that's the engine test lab you can see there with the students working in the top right corner there. And there are other labs as well where you have material characterization, which is that we have what's called the Brunel Experimental Techniques Center, ETC. It's a research center where you can characterize all sorts of materials. You have scanning electron microscopes. You have all sorts of other, equipments there as well. You might use them or you might not. Depends on, of course, your activity during your program or during the program here. Okay, just to give a flavor, I suppose, as to the types of projects you can have. I'm just going to talk about two here. Just to give you an idea when we say a research project. So this was a project I wasn't involved in, but it's a project that is focusing on computational modeling. So here the research is trying to look at a new method, which is called macro element models, and trying to compare this macro element model technique with high fidelity modeling or high fidelity finite element analysis. Finite element analysis is considered high fidelity modeling. And this is for crash optimization or for modeling the crash of the car. So you can see the car there, the airbags deployed, and the passengers there certainly elevated off the seat because of the impact. And the whole crash process we're trying to model that. Now, in FEA, this is a very slow simulation. We can certainly predict it quite accurately, very accurately, but it's a very slow simulation because it's high fidelity. We model all sorts of degrees of freedom, millions of degrees of freedom, and it's dynamic. And we, of course, we have very short impulse times as well. So that can take weeks. So I've had FE simulation that taken months before. But this macro element model is one that can basically reduce this from hours to seconds. Or if it's taking weeks, then it can reduce it to perhaps a day or so. But the question then remains, how accurate is it compared to FEA, which is the benchmark? So you can see the comparison here, where this is the normalized force, impact force, being measured in the simulation, from the simulation. And you can see there that it follows the trend. There are some deviation, but it certainly does follow the trend, which is quite good. And that confirms that this simplified or reduced order model certainly is fit for purpose and is able to model the impact process. Now, this is a project that I was involved in. I was the supervisor, and it was a master student, and he was looking at the diffuser of a Concorde engine at the inlet. So when you have an engine, either a jet engine or a Concorde engine, what we have to do first and foremost is to let the air in, first of all, and then we compress the air, and then we feed that to the combustion where we inject it with fuel, and we combust it to add more energy, and then we exhaust it to create thrust. Of course, the flow velocity is increased, and then you get some thrust. Now, for supersonic aircraft, it is going higher than the speed of sound. So you can't really quite feed that into normal compressor as you would for a normal jet engine, because what that means is you'll get all sorts of shockwaves forming everywhere, and that's just going to be highly inefficient and very, very problematic for the structure itself. So this student, what is done is to design a diffuser, which is a ramp, that creates a series of shock waves. And every time flow goes through the shock wave, the pressure goes up and the flow speed goes down as well. So it's slowing it down and it's also compressing the air. So it's doing the job of a compressor. But it's not doing it with fans, it's doing it with a ramp. So the student's project topic was to design that ramp. for a given flow condition. So he did all of this using CFD simulation, and then he used the supersonic wind tunnel here, which is shown that's the supersonic wind tunnel in the corner there. And he 3D printed a part, very small working section. So he 3D printed a very small part. We can scale things down in aerodynamics. That's easy for us. You can see his design there. And this channel is what he modeled in the CFD, which I've got the video showing his simulation. Now, what he was trying to predict is, with his design for the ramp, he's trying to predict the shockwave angles that forms, and those shockwave angles need to form in a precise position to make sure that they first and foremost compress the flow very well with very little loss in the total pressure, and also to make sure that the shockwave doesn't continue into the engine as well. So he's got the flow develops. As I said, this is a Mach 2 wind tunnel, 1.8 wind tunnel, approximately Mach 2. So I'll play the video, and you can see the flow develops is going from the left to right. His object is in there. The flow develops. You have the Mach number here. Apologies, the student didn't quite do this very well for you to see the numbers, but he's got there as well the actual Mach number at the region of the object. So the contour plot is of the Mach number, as I said, and I'll just let that flow develop fully. And once it's fully developed, you'll see the shock system that forms around the inlet, just around about there. Yeah, so that's formed. And you can just about see the shock waves that's formed. More particularly, he was interested in this region. And then what he did after making this prediction with his design was, as I said, he made it and then went in the wind tunnel and then compared the predictions with the measurements in experiment. So that's a typical sort of MSc research project, individual research project. Those two are, one is more structural, one is more fluids. Now, we do have group projects, as I said, and I'll also link it to what I call special features. So we have a group project, which is a project that's aiming to design an unmanned aircraft system. So UAS. So UAV wouldn't be an unmanned aircraft vehicle, but this is an unmanned aircraft system because it has to be autonomous. So it has to be unmanned and it has to be autonomous as well. So you can't control it yourself. So from takeoff, you have it on the runway, you turn it on or you start it off, and then you leave it, and it does its mission that it's been programmed to do. It is led by the IMechE. It's part of what's called the IMechE UAS Challenge. And what we have students leading this activity. So they form a group, and it's led by the MEng and the MSc guys. So, the master students, they form a group, and then every year they make a group and they have to design the aircraft. It's part of their project, so it satisfies the academic requirement. But also the IMechE challenges itself as a competition. So what they do as well is to enter this into a competition, just like your Formula students competition, but this is for aircraft. Okay, so I've got the pictures there, which shows the first year. This was the design for the first year, and then we have the design to the bottom right for the second year. Worth mentioning that actually in 2019-2020, this was the year of COVID, they won an award for safety and airworthiness, and they came 6th overall in the competition. So every year we've been entering for this, which is quite a good thing. So it's a special feature as well. Apart from the fact that it's a group project, it is also a special feature because it's quite fun, I think. And it's just that place where you can bring together everything you've learned, in your program. You can bring it all together into this one project. So here I've got the pictures of students building aircraft there. Some of us are still wearing masks then, because we're still in COVID, or at least we're coming out of COVID, should I say. So So this was the aircraft for 2020 to 2021, I believe. I've got the one for 2021 to 2022. I think this is the next slide. Yeah, so this aircraft here, the white and blue one, this was the aircraft last year. And you can just see them side by side there. So it's much smaller for the aircraft last year. The aircraft 2 years ago was just quite big, actually. And I've got a nice video that shows you last year's aircraft, and it shows you flying as well, which is beautiful. Yeah, these are the students. Before I show the video, these are the students on one of their flight tests. So we have a field that's owned by Brunel. It's part of Brunel campus, and we test flight there. These are the students at the competition, and this was the aircraft in mid-air during the competition. And I'll just play this video quickly.
Say green light.
Oh, right. I just stopped that mid here. But yeah, so worth mentioning that the students every year they come up with their own design. So they don't have, I mean, of course, they have the report from the previous year, but they need to come up with their own design every year. And so they build that, they go through the whole design loop and build it and then test it. And we have all sorts of things go wrong sometimes, but then they learn from that. Of course, we do have the formula students as well, which is ongoing. It's not necessarily, you know, within the aerospace program, but what we do have is we have students in the aerospace degree helping them because, of course, you have to look at the aerodynamics of the formula car. So I certainly supervise students year on year who are modeling the aerodynamics around the spoiler, for example, or the front wings. We also have a bike car, which looks at designing an electric bike. Again, it's part of an IMEC competition as well. Every year we do run an event which is called the Brunel's Engineer, where you get to showcase your project to industry. And it's an evening event, and it's quite nice because you've been working so tirelessly on your project. In the evening, you can either showcase if you have something you've built, which tends to be the case sometimes and often, and you have industrial partners or industrial guests come round and look at your design, and awards are given as well at the end of the event. Okay, moving on quite quickly. I'm just mindful of time. So Brunel, the other thing as well. I mean, of course, you have fun in your degree. It's part of our passion, what we do, but you do have to look forward to when you leave Brunel, and that's about employability. Again, Brunel actually does quite well there as well. So quite recently, we had the news that Brunel was ranked the 14th best university in the UK to produce the most employable graduates. So another statistics that's quite promising and is quite good, and it just reflects what we do at Brunel. So we have a whole team, a whole center dedicated to professional development, the PDC, Professional Development Center. They help with all sorts of things. They organize career fairs, number one. They help with CVs. They help with interview skills, all sorts of things. Whether you're doing a test for your interview, they can help you with that. A wide range of things, and that's available to you as a Brunel student. So that brings me on nicely to actually talk about some of the places our students go to. So where we find our students going are places like Airbus and of course Virgin, Heathrow, all these other places. These are all the typical places our students end up going to. So I hope this has been very informative and hope you've enjoyed the talk. Yeah, and hope to see you at Brunel. Thank you.